So hi everyone, I'm Kawamura from IPGP, and today I'm so excited to show you some of our ideas to our seismic exploration of the moon on behalf of our team. So next slide, please. So first of all, I would like to start by saying why we want to do seismology, and this is because we want to know what is inside the moon. So we want to know the internal structure of the moon to understand its origin and evolution. And one of the great example we have right now is NASA InSight mission, which landed on Mars and carried out 4 years of seismic observation on Mars. And this mission was equipped with the first time the broadband seismometer, which enables us to observe long period seismic signals. And we were able to really define a so-called textbook image of Martian inner internal structure, as you see on the right figure. So this is exactly why we want to do seismology, and we really want to pin down what is the internal structure, what is the structure of the crust, what is the crust structure of the core of the moon. And this is exactly why we really need to go back to the moon with the seismometer. Next slide, please. So there's various key questions that we want to address, but basically the idea is to, by understanding the internal structure of the moon, we really want to understand the origin and evolution of the moon. So here I took, summarized some of the scientific themes that Ultimate 3 Scientific Mission team reported, and many of these themes that is related to the lunar formation or lunar differentiation is strongly related to seismology. And here, I think you can already pick up some words like lunar core, crust, mantle, which is exactly the thing that we want to explore by using seismic method. Next slide, please. But of course, we are not the first one who will be doing the seismometer, and we have already some data from Apollo. So here is a short summary of what was done by Apollo. So Apollo was mission with five seismic station, of which 12 to 16 consist made the four seismic station, which made the seismic network on the Apollo. So this is exactly the first and only extraterrestrial seismic network we have on the moon. And this observation really was a huge discovery because we found that the moon is seismically active and there's many seismic events on the moon. And this really led to the better understanding of lunar internal structure. Next slide, please. So here I'm showing you some example of moonquakes. So there's many different kinds of moonquakes, like deep moonquake, shallow moonquake, meteor, and which was already very surprising because before we thought that the moon was a dead body without such activity. And we also detected many meteorite impacts which shook the lunar surface. And where I want to draw your attention is that when you see the seismic signal, it's really it has very long ringing characteristic long ringing coda, which we will not see on the Earth. And actually, this is what makes lunar seismology so complicated because this masks all the different kinds of seismic signal such as reflected phase or refracted phase. So we really want to avoid such effect of coda by using a broadband seismometer and observing this in a long period so that we don't see this effect of scattering. And this is exactly what we want to do for the next observation. Next slide, please. So here I'm showing you a current day understanding of lunar internal structure. So if you see a figure like right top, you might have an idea we really know very well the internal structure of the moon, but this is not exactly the case because if you see on the left figure, so this is like a summary of the best effort we made to understand the internal structure of the moon. And the top gives you the full structure, and the bottom one shows the zoom on the shallower part. And what we can see from here is that while many models agrees globally in terms of structure, we have still lots of uncertainty, especially on the deep region. For example, the we still don't know what the core structure is. Do we have inner core or outer core? This is still open, and we really need to pin down such the structure deeper than I would say 500 kilometers to really understand what is the structure of such a partial molten layer or the core, which has strong impact on the content of light element inside the moon. And I would like to also point out that even for shallow structure, we still have a debate if there's, for example, a low velocity zone around 200 kilometers. This is very important because this will be constraining the dynamics of internal dynamics inside the mantle, which will be constraining the activity of the moon today. So these, while we have some very global, very general idea of what the internal structure is, we still have many details to be constrained. Next slide, please. And another thing is this 3D structure that we still don't understand. So it's widely known that the moon has near side, far side dichotomy with near side with thinner crust and far side with thicker crust. And we also know in terms of seismology that many of the seismic source is focusing on the near side. So we still don't know if the far side of the moon is still seismically active today. So I would say one of the key questions we have is we have to understand the dichotomy of the moon in depth. In other words, how deep the dichotomy of the moon stems is the very important question we would like to address to understand better the origin and evolution of the moon. Next slide, please. So for this, what we need is a network equipped with broadband seismometer. So here I'm giving you some of the ideas or some of the constraints I will say we have for the lunar seismic network. For example, we have to have global network. We don't want to have some station that is focusing on one part of the moon and which is globally distributed. And these should be equipped with broadband high sensitivity broadband seismometer. And finally, we would like to have long-term monitoring of this because seismology, by definition, we really have to wait for a large event. And if I were to give you some example, Apollo was 5.5 year of network observation, and InSight was 4 years. And this was very important in terms of science. So we really have to we want to have a long period, continuous monitoring of seismic activity on the moon. Next slide, please. So for this, we are now developing a new generation seismometer, which is an optical seismometer. And by moving to this optical technique, we were able to reduce the mechanical noise of the seismometer significantly, which is really the game changer in terms of seismic observation. So on the bottom figure, you see that we are using the interferometry technique to detect the small displacement on the ground, and we are also developing the autonomous survival module, which will enable us to place the seismometer and continue the observation even after, for example, the lander stops its activity. And the idea is to demonstrate this in a 2028 precursor mission, which we are now preparing for the launch. Next slide, please. Yes, so finally, I would like to mention some word about the mobility and the seismic observation, and I separate this into like a local, regional, and global scale. So I would say that when I say network, it's rather something distributed globally. So if you see the right figure, it's the world map. So if I were to say the network, we would like to have something global. But at the same time, mobility in the regional scale, which is about like tens of kilometers, will also be interesting because this will help us not only constrain the local structure, but this can also help to go to global structure by using the correlation between separate stations. And next slide, please. Yes, and I would say we have never had a better moment to push for this lunar seismic network idea because we have a high TRL observation system with the various launch opportunity, including national ones and private ones. And finally, we have the community that really supports this. So I would like to really push on this idea to make this seismic network, of course, with Japanese contribution as well as international collaboration. Thank you very much.